knowledge. Dr. Sutton studied his doctoral degree at the University of Illinois in the Department of Theoretical and Applied Mechanics in 1981. And in 1992, he joined the Department of Mechanical Engineering at the University of South Carolina, and he's been a professor there since that year. Currently, he is a Carolina Distinguished Professor in Mechanical Engineering. I was president of SEM in 2001 and 2002. Okay. And he has received many honors and recognitions for his scientific work. He's a very prolific author. He has authored more than 170 journal papers, several chapters in books, and he wrote the first book on image correlation in 2009. His current research interests are in experimental and analytical fraction mechanics, applications of computer vision for high-rate events, and biomechanics. His wife, Elizabeth, they have 2 children and 2 grandchildren that were born in 2011, and they are fraternal twins. So they're very proud grandparents of 2 beautiful grandchildren. Michael is going to talk to us about the recent increases in computational speed and memory and how this transforms the way in which we acquire and store data, which has resulted in very robust, accurate, and very fast vision-based non-contact methods. But I want to let Michael tell us the rest of the story.
Well, it's my pleasure to be here and to talk about 30 years of work. And so let's get started on that. This is the outline for the talk. I'll give a little bit of background for the acknowledgments, some of the background on the method, and how things evolved in this time between measurement methods, simulations growing worldwide, and then how DIC came about in the process. I'll briefly go through the 3 methods that really form the foundation for DIC. With volumetric digital image correlation, also known as digital volume correlation, being a more recent entry into the field. I'll give you a brief summary of selected correlation methods and how they've been used in a variety of applications. And then I'll focus on in more detail, show the robustness of the method for these applications. And finally, at the end, I want to talk a little bit about, I think it's important to talk about where we're going to go, and I'll give you my perspective on where things are going, both in design and development, which is not really the focus of DIC, but it's an area where it could be potentially used very impactfully, as well as just trends in the DIC methods themselves. I'll end up with a summary and then a list of the students who have been involved over the years. Must put up a list of the people that have sponsored the work over the years. I particularly am grateful to Dr. Oscar Dillon, who gave us the first start in the method back in the 80s. And Oscar's still alive and living in Kentucky. Charlie Harris, former director of research at NASA Langley, and some of the folks at NASA continue to support us over the years. And you can see a list of other people, including Dr. Stargell, who's still at AFOSR, as well as a couple of folks that are here today, Phil Roy and Tim Miller. We had a few industrial support over the years, including Dr. Zavatieri, who's here now. He's a Purdue professor, and Ed Ingram, who's still a senior research fellow at Lockheed. I got to put these up. There's too many names here to go through the details. I've worked with a lot of folks over the years. These folks have been very helpful and very supportive of what we tried to do with DIC. and some of them are here today. You'll see names like Hugh Bruck and Bill Forney and others scattered through here because all of them have been involved in another. Wish I had time to go through all of them, but can't. So let's get into the talk. We'll start first about the, as all of you know, most of you know anyway, the early years were focused on point-wise measurements, from strain gauges to rulers to calipers, whatever. Point-wise measurements were the common approach. And this lasted all the way into the mid-20th century. At the same time that this was going on, photoelastic methods began to be used significantly. Chuck Taylor, Jim Dalley, a variety of people used photoelastic methods. I still remember the set of local stress freezing slices that Chuck Taylor had in his lab at Illinois. There are advantages and disadvantages to each of these, but as those were evolving, along came the laser. And the laser changed things. I was at the end of that era, but in the 60s, the laser came along, and out of that came interferometric methods, from Moiré interferometry, speckle shearing interferometry. All of these methods took over in the lab for a while. And during that time, all the recording was on film. Its own issues. In 1980, a paper that I continue to recommend to anybody that wants to talk about the speckle method is a paper by Vince Parks. Vince is no longer with us. He wrote the paper in 1980, and it shows very clearly the limits that you can go to with speckle photography, and specifically what he was focused on. Here, if you move too far, you rotate too much, and it's all small deformation, you lose coherence of the laser speckle pattern. As a result of that, when you try to reconstruct the deformations, it doesn't work. Before that, of course, it's fine, but all of that required that you be careful about your deformations, and large deformations, including out-of-plane deformations, simply weren't tolerable. The film process, I guess most of today's folks don't even worry about. But I got to talk about this because in the early years we had to deal with these things. The nonlinearity of the film was a real problem. Film processing was done in the middle of the night when you hadn't had too much to drink. Film stability and handling was all an issue. You had to be sure that you kept it stable. If you put it out and it began to warp and distort, how do you connect that back to the original shape it was? Decorrelation effects we talked about earlier, and all the things that go along with trying to reconstruct from a piece of film what was going on. We eventually went to glass slides. Glass slides are fairly stable, but they also have their own issues. As a result of all that, people were always looking for ways to get rid of film. And I was in the early stages of that, and one of the people that tried to find ways to get out of it, because it's a problem. While this was going on, many of you recall the computational methods were taking off. From the Nastran to ANSYS, you name it, people were developing codes all across the world. And those codes were being used to solve very complex problems. And they could do them robustly. And they did that on a consistent basis year after year. And as the codes grew and the complexity of what they could do improved, experimental methods began to become less and less relevant in that scene. People saw ways to try to make measurements, but they were difficult to do. And we still did them, but it was hard. And at some point in time, people began to ask the question, is it more economical simply to run simulations and to minimize as much as possible experimental work? In fact, in the late 19th century, there were national labs that actually were thinking seriously about replacing experimental methods with full simulations. Here on the right is a simulation of stable crack growth under mixed mode 1-2 loading with the crack growing in mode 2. It looks beautiful. And quite frankly, this matches the experiment quite nicely. But that's not always the case. And we all know that issues such as boundary conditions, material properties, you name it, environment, affect the results. And as a result, it becomes very to simply use a set of simulations to predict the future. During that time frame, computer technology continued to grow, and with that came the foundations for growing something like digital image correlation. A method used the same computer technology to drive an improved method for making measurements. And that's where it came from. In the early years, in the 80s when this started, they were extremely slow. And there's no doubt that, in fact, the first time we ran a correlation, one subset, 31 by 31, took 30 minutes. Well, that's gone. We all know that's history. Today, you can do thousands of subsets in a second, and as a result, the method becomes very, very practical for a wide range of complex problems. In 2011, I was at a conference in Belgium, and I wished I remembered his name, but I simply can't remember it. A computational scientist made the statement noted here. He said, for the first time in 30 years, experimentalists can take more data at a faster rate with higher resolution than computational methods could. And as a result, the question he was referring to here was he was actually referring to 3D DIC. But it gives one pause about what the future is going to be. How will computation and experiments in solid mechanics and related disciplines evolve in the future? How are we going to use them? How are we going to take all this power and use it in an effective way? This group here, as well as others, uses it every day for a wide range of things. In a broader sense, what's going to be out there? Where is it going to go? And so part of what I'm going to do toward the end of the talk is give you a little bit of what I think is going to happen. Now, the history of this for DIC extends back to 1980. As best I can tell, Dr. Ranson and Dr. Peters were the first, and you see him over here, and Dr. Peters still looks like that after all these years. They were the first two to really put out the initial theoretical paper. I came along in '82 and began doing work in the lab with Phil Chu. Philip was still a graduate student there in the year that I was there before he left, and we did some of the early experiments that proved that it was feasible to do this. And we did basically translations in strain. And you can see at the bottom, this very simple. This is a piece of rubber, and we simply stretched it with this dial chronometer here that told us, the micrometer told us how far we were rotating it, and that tells us how far it moved. And we compared the displacements from the theory and the experiment, and they matched pretty well. So we began to ask the question, could we not do this? And we used a white light speckle pattern for that. Hugh Bruck made a significant contribution in '89 when he developed the Hessian-based approach for improving the speed of the iteration. And that was really important. We still use it today. It's one of those things that transcended the simple approach that we used then and is used in all sorts of DIC from 2D, 3D, and volumetric. Others that have participated along the way include Dr. Luo from Taiwan now and Bill Chow. They were early on involved in the stereo stuff with me. So the 3D DIC came along between 91 and 93, roughly. Jeff Helm and Steve McNeil and I worked on, in 96, on robust stereo vision. Robust, it had to get out of the lab. We couldn't simply do all this stuff on a laboratory basis. We wanted to go to the field with it. And so they developed part of the methodology that we use today to take it out of the field and make it usable elsewhere. We actually did some tests in '97 on a Boeing aircraft in the field in Seattle. So with them, we knew it was going to work. In 2000, Brian Bay, who's listed here at the bottom, was the first person I could find that did volumetric DIC. Direct extension of 2D, but he actually did it for bone. And he showed it would work in volume, and today, I firmly believe that's one of the growth areas. It's going to continue to expand as the methodologies to acquire volumetric images continue to improve and are reduced in price. Okay, so that's kind of the background. Where do we come from? 2D DIC method, which is still used today in specific applications. I'll briefly talk about it along with the others. I would mention up here you'll see some small boxes with a number in it. Those are references that are at the end. You won't get to see them for now probably, but if you ever want a copy, I'll be happy to give those to you. And we're actually going to put it up on the SEM website so you can download it. And the references will be in the back. Okay, so the 2D DIC method, this is an early version of it. You have your monstrous computer of that time with a CCD camera. And we have some lights. And we talked about lighting earlier in a panel discussion for high speed. But the typical lighting back there was just whatever we could find. And the specimen was typically oriented about 90 degrees with some sort of a white light speckle pattern on it. Uniform illumination is not required, but it would be helpful. The main thing is to have good contrast. And you have to, for this to be effective in a broad setting, it has to be loaded in plane. Typical approach that all of you use, you deform the pattern and you end up finding subsets before that you select, you find them after, and you find the displacement field associated with that deformation. There's all sorts of mapping functions that have been used, assuming the shapes of the subsets, and those are in the literature today. The bottom line is it works really well for 2D. And we obtain full field deformations with this methodology by using a whole range of subsets scattered across the entire image. You can correct for distortions, typically not, because most cameras are pretty good, but it's feasible to do that with no problem. Here's a simple example. In this case, we see this all the time. We have a plate with a hole. In this case, it's a rubber plate to give a lot of deformation. And you can see the fidelity of the deformations that you can measure. This is the horizontal displacement from low on this side to high on this. And this is the transverse displacement with the contraction inward here and the contraction inward here shown up clearly visible in the measurements. The noise here is quite small. And as a result, the method works really well. I do need to go through, in each of the methods I'm going to go through this, what are the things that I feel are important to know about them. It's fairly simple. That's why everybody uses it. Okay? You can use it in the field as well as in the lab. Putting on the pattern is not difficult except at the microscale. When you get down and you're trying to put on nanoscale patterns, of course it's more difficult. But in a general sense, there are a lot of simple methods to put on patterns. The data acquisitions are well established. We have codes and vendors here that do that all the time. We've made measurements for a wide range of specimens. The 2 meters I've done personally. People have told me they've done 10 meter specimens. I've not done that, but I've done them from 10 microns to 2 meters in the laboratory. It's about near real time. You can run 15,000 subsets per second. Francois Hild and his colleagues actually wrote a paper about controlling test frames using data because it's so fast now. You can actually test certain conditions from DIC. Strain levels over 1,000% have been measured. That's right, it really is 1,000. You can stress these out until the contrast is lost and you can still track them with viable code. Variability less than 0.01 pixels is common. Typically 5,000ths of a pixel is the variability, and that typically comes from noise in the cameras. If the cameras have low noise, you get improved accuracy. 100 microstrain is common for you can do much better than that if you're really careful, but plus or minus 100 microstrain will certainly cover most of the cases. Out of plane displacement can be handled. You'd prefer not to do it using standard equations. So it's recommended that you not use that if you have large changes in out of plane displacement because you'll get defocus or pseudo strains unless you correct for it. And that's one of the limitations for 2D. It really needs to be an in-plane deformation if you're going to use it. But there are a wide range of cases that are using this, even today. We've used it for off-axis tensile loading of planar composite specimens. And NASA has several setups to do that. We've used it up to 750 degrees myself personally. Other people say they've done it to 1,000 and more. I haven't done that. I've used it up to 400 hours. So it stayed in the furnace for that long. We acquired data during the entire time to look at the creep response. We've done it with optical microscopes, and we've done it both with SEMs and AFMs. So the scale that you can do that at is what is important about DIC. There's a range of scales that you can do it. Down here, things become more complicated. The imaging method is different, the distortions are different, and you have to handle those. But it still is doable. Because of the out-of-plane issues, in the 90s, we began to push towards stereo. Now, stereo vision has been around a long time, folks. It goes back to the 60s. It goes back to people that were doing it in the computer vision community. But they weren't interested in doing it extreme accuracy range. They simply wanted to know where something was, plus or minus a couple of pixels. They wanted to know where it was going. The scene itself was what was relevant to them. So our task was to try to take those ideas and convert them to something that could be used for strain measurements. So here is a simple setup. The setup itself basically looks at a specimen that has a pattern on it. The pattern itself looks just like the one in 2D, no different. And the idea was to extract information from this by taking the views before and after deformation, using standard formulations for stereo vision, and extract from that the data we're looking for. Here's the procedure in a simple sense. As you can see, you take one of the cameras to be the reference. As it deforms to a new position, this and this are compared. And the same way with this camera, and then you cross-compare these to try to find this same subset in all three views. By doing that, you then extract the information you need, and you do this really fast today. The mapping function generally is projective to account for the perspective distortions that you have. They go back to the days of Leonardo da Vinci, who was one of the first to actually talk about perspective distortion. So from this, you can measure all three displacements, as you know, and we can use those to extract the strain fields in the surface. Here is an example of one of the early ones. This is after Dr. Helm, Professor Helm, and others were working on this to put it in the field. Here are the two cameras. It's mounted to a gantry in a lab at NASA. Over here is the specimen, which is a large plate speckled on the bottom with a crack right here. As we loaded it in tension, around the crack, it buckled on the bottom. That buckling was of interest because they're trying to determine what is the state of stress in the vicinity of a highly buckled crack tip region to be sure that they understood what fracture parameters would be appropriate. So out of this, you can measure, in this case, this is a few millimeters, 12 millimeters approximately. The scale here is about 500 millimeters, half a meter across. And the accuracy was quite good. Matched very well with fine element that we did later. Well, this one, 3D DIC is probably the standard today in many cases. Full three-dimensional displacement measurements are obtained in both laboratory and fields. I've personally used it in the field on several occasions, including tanks, large water tanks, and other cases similar to that, just to measure deformations during the filling and the draining of water tanks. You can calibrate this thing fairly simply now to get the parameters you need to actually convert the images into 3D displacements. The data acquisition procedures are well established. You can do curved objects and large objects up to 10 meters, and small objects on the order of a few millimeters or smaller today. Remarkably, this is even faster in some cases than the 2D. You can do 50,000 subsets per second in some of the codes today. It's unaffected by large rotations. You can rotate them a substantial amount and you still get back out the strains you're looking for. And we also did this in a microscope to confirm it was also viable in microscope systems. The accuracy is quite good. I didn't report it here, but it's on the order of 0.01 pixels again, which is quite good. The strain is again on the order of 100 microstrain. And that's point to point across the field. The volumetric method was developed by Brian Bay and his colleagues. I want to talk briefly about it. As you know, it's different. It's different in the sense that you typically have some sort of source. Here I'm going to talk about CT. I'm not going to talk about confocal or MRI or other methods, PET scans. All of them have been used. I'm just going to talk about CT today. So in essence, you reconstruct through a series of rotations and images at different angles of the specimen relative to the X-ray source, and moving this up and down, you reconstruct the entire volume in terms of an intensity difference or density difference across the field. The raw data is stored for each line and rotation angle, and that's transferred to some sort of a reconstruction algorithm that converts those individual scans into reconstructed volumetric images. Those images are then compared before and after deformation on volume, inside as well as near the surface. This approach, Brian Bay showed, works really well. Here's the approach in concept. Here's the entire region that you've converted to an image. Inside of there are what we call voxels. Just like pixels, they're voxels. Those voxels individually have a density. It's the average density extracted from the reconstruction algorithm over that region. And the whole region is converted into however many, 1,000 by 1,000 by 1,000 voxels. or if it's just 8 bits per each one, it's a gigabyte of data. That gigabyte of data is stored before and after deformation, and you extract subvolumes for that to compare between the deformed and undeformed. So the same procedures that we use in 2D follow directly to 3D. Even the interpolation algorithms are just direct extensions in most cases. Here's an example for you to look at. We did this about a month or 2 ago at South Carolina. We have a disk that we put in compression. Here is one of the layers. Here it is unloaded. Here is that same layer after it's loaded. And you can see how it's been barreled and distorted due to the deformation in that region by the compression. Here is a layer down in the center. Before, you can see the speckle pattern that we're going to use embedded in there. And here it is slightly barreled and distorted again in the deformed state. So, in this case, the disc was 2 inches in diameter, ½ inch thick. The white particles are sand. The rubber matrix is surrounding it. So we embedded a sand particle grouping in a matrix of rubber and used that for our experiment. And here's what we get when we compare the experiment to the theory. We also got the material properties for the as particulated component, which was different than the rubber. Okay, so we actually got those properties from independent tests, and if we take a line vertically, we compare them. The FEA and the experiment matched except for one small region where the code got lost. This region was in a region that was too densely packed with sand, resulting in a inability to find the right location. Here's a cross section through the center, a line across, and here's the theory and the experiment. The experiment is the dashed line, the theory is here. So it does really well. And in this case, this is the horizontal displacement, and this is the vertical displacement along here. I have a video to show you more details of this same experiment. The color scheme is different, but it shows you just how much you can do with this. And notice how you're getting data all the way along the length, and then we'll do it across in both directions. And you can see here, if I stop it for a second, well, I'll just let it go. You can see that this is almost a 2D problem. Things look the same in 2 of the directions. So the data you get is extremely dense in this case. Turns out that the data matched really well with the fine element analysis. What can I say about this? The one issue is you got to have a volumetric image system you have to understand. If you're using confocal, Professor Ravi Chandran at Caltech wrote an article explaining that you have to correct the images because of the distortions introduced by the imaging process. There are distortions that you have to account for if you're going to get accurate data. I think you did that with Professor Frank, who's now at Brown. The pattern generally comes from internal sources unless you seed the material, as I did. When you seed it, you change the material. You have to understand that, of course. Image acquisition is slow. The data you just saw took 4 hours to acquire each set of time to get high resolution results in laboratory level devices. I found that the noise levels are pretty high. I got 3% noise, and I thought that was excellent. That means the intensity pattern is 1,000, then you have 30 gray levels of noise just scattered in there, everywhere. And that can cause problems. That's at the very high end for camera systems. DIC camera systems that we typically use don't have that level of noise. Data acquisitions are well known now. There is a problem with artifacts due to the imaging process. The reconstruction algorithms used will introduce artifacts. Unless you want to change that and write your own, you have to deal with those. We can get this for small or large specimens. The smallest I've done personally is 10 millimeters by 10 millimeters by 10 millimeters. I've seen others that have done far smaller than that, but that's the smallest I've done. The images are large. You do need if you're going to use standard CT imaging systems with standard reconstruction, they're big. You got to deal with that, and memory management becomes a problem. The accuracy is pretty good. It's unaffected by large rotations or translations. If you have a good initial guess, then all you can do is just run through the analysis very quickly. Remarkably, 5 thousandths of a voxel we've obtained recently. So it's very, very accurate on top of this. The issue, of course, is getting good contrast. Okay, so that's the methods. Let's show you some of the examples that we've done in recent years. Here's one where one of my favorite, quite frankly. We did a lot of work on ductile tearing in mixed mode. And the shape of this, the heavily distorted shape, comes from Jeff Helm, who did the work years back. And we can see that our fine element analysis, which is here, matched pretty well in general shape. And the crack in this case was curving under large deformation, and we were seeking fracture parameters that worked under mixed mode conditions, mixed mode 1-2 and 2-3 and 1-2-3. Turns out it works really well with COD. That's the one we found worked well. Here's some thermal strain measurements at 10,000 X. Field of view here is about 40 microns by 40 microns. You can see the type of distortions that you have to correct for in a scanning electron microscope. If you don't correct for those, they add error. That's error in your data. This is not strain induced. This is because of the imaging method. Down here we see the strain fields that come out after you've done the calibration, and the errors are on the order of a few hundred microstrain. So it's pretty good once you've corrected for things by removing these distortions. We found that averaging of images was extremely helpful during that stage. We've also been recently working on carotid arteries and looking at atherosclerotic plaque rupture. I have a video of an experiment. It's not necessarily pretty, but it's before lunch. So I think we're okay. And you can see we're removing the plaque over here from one of these small animal artery specimens. And as we do this, we recorded not only the area of this, but we recorded the displacement along this direction using DIC. In this we used a point matching approach instead of a pattern to extract the displacement for comparison to the other. Well, and over here you see the energy release rates for two different types of mice. You clearly see differences, and we continue to look into why that's the case, because it's important in trying to understand what sort of treatments you might be able to develop. At the same time, we also been looking at 3D DIC for arteries, the outer surface. The video that I took at the bottom, it's very small. What we were interested in is it uniform as we pressurize? And what we found is the arteries are not uniform. They do not deform uniformly. The left end was completely free, and it actually bends and distorts instead of simply pressurizing like we expected. Because of that, we continue to work on this, and these are extremely small specimens. Notice this is only 0.4 millimeters in diameter and 3 millimeters long. So these are very challenging experiments. Notice the pattern on here. The pattern is beautiful. It was done by cellular stain, in this case, to acquire what we used as a pattern. Very, very nice pattern. We've also done a lot of work in theoretical developments in air analysis. Large number of recent articles by Phil Roy in Experimental Techniques talking about methods for minimizing error and improving the accuracy of the methods and how to do it practically in the field. Early on, in the last few years, we were interested in trying to extract quantitative measures for that. We've actually developed a flow chart for how to calculate parameters that tell you the error in a real experiment. And over here we found that the variability matched accurately between the theory and the experiment as a function of noise. Here is 3% noise in a camera. Right out here, it's hard to see this from the back, but this goes from 0 to 3% noise. We don't see cameras, CCD cameras out here. They're typically down in here, between 0.5 and 1% noise. So down in this region, the theory and the experiment match really well. Recently, one of my students and I have been working on looking at particle tracking in fluids by taking cameras outside and looking inside. And we developed the equations for that using previous work by another student, and it works really well, and the accuracy is quite good. Down here is the theory and the experiment for particle tracking in a viscous fluid. Okay, so that's the kind of things that's been done for it. I want to talk a little bit more in detail about two applications. And the reason I'm going to show these is because they show the power of the techniques. In this case, it's going to be 3D DIC that we're going to talk about. I'm going to talk about a woven epoxy composite under combined compression bending. Professor Riefschneider at my place asked me about 3 years ago, could we do this? Could we take small specimens of a specified composite material and subject it to large deformations, measure what's going on, and use those to see whether or not we could extract damage criteria that we could use? So I said, we'll try. And so we've done that, and I'll show you briefly some of the stuff we've done with this. This briefly says the same thing I just talked about. It turns out that the 3D DIC method is particularly well suited for this, because as you bend it and compress it, the deformations become extremely large. And yet the specimen survives. It is damaged, and the question is, what can we tell about what happened to the specimen? Here's the specimen down in the corner over here. We're going to have fibers that they're orthogonal fibers, and we're going to cut them out at different angles and bend it along this axis. So it'll be under compression and bending about this axis right here. So it'll bend outward from here. The pattern is shown here. It's not showing up very well. There are 6 layers, and it's a woven material. So the woven part is important because it really lasts a long time. There's no delamination. It stays together all the way up to the very end. The material is from a particular vendor that has a long relationship with USC and likes baseball. Don't ask me why that's important. The setup is here. It looks like the same gantries that Dr. Helm used years back. We have 2 systems, one on this side, one on that side, looking at the specimen that's going to be compressed here. We modified it slightly because it bends so much that we had to tilt the 2 cameras on the tension side and the compression side so we can keep this in focus for a longer time during the bending process. As a result, we had out-of-plane motions of 40 millimeters, yet it still worked remarkably well. On the compression side, we rotated the cameras 20 degrees counterclockwise. On the tension side, we rotated them 20 degrees clockwise to keep it in focus throughout the experiment. Here's some of the results we got. Another video to show it. Some of these things, some of these things are best shown in video. Over here on the left, you'll see the load going up, and now they separate for the different fiber angles. The load now is continuing to be fairly stable in some of them and dropping in others, but the deformations continue to be measured accurately. This is the out-of-plane displacement for the 3 fiber angles. And this went all the way to failure, okay? We kept getting quality data all the way out. The strains here were on the order of 7 or 8%. They weren't huge, but the displacements themselves were extremely large. And here, the only thing that got in the way on the far right was the grips themselves. We simply lost the ability to see it because the grips got in the way. I had a chance for the first time to compare my results to one of the founders of solid mechanics, as far as I'm concerned, Dan Drucker. Pulled out one of Drucker's old papers from the 50s on how to analyze fly rods. That's right, fly rods. And out of that came a set of equations that we modified for our case, and we compared to Drucker's original equations for the case of 0 and 45 degrees. Of course, Drucker's equations were not for composites, so the 45 degree was just an average value of the modulus for a 45 degree case. Because it's displacement controlled, you can see they matched up very well. Here's the strain, and this was more interesting to me. The strain that we saw for the 0 degree case from Drucker's equations and ours matched pretty well. Drucker's equations theory is the red line, and ours is the other one. We noticed a difference at the very top, you can see, for the compression side. The yellow circled region here is on the compression side. The strains were higher here by a considerable amount, and we found later by analyzing it that was caused by buckling. The fibers themselves buckled out of plane, causing larger deformations there than we were measuring on the other side. So there's a direct connection between the data we got from the DIC method, which continued to work even though we had buckling of the fibers, continued to make measurements, but microscopically things were failing. Last one for this that's very useful to see. We're particularly interested in the critical regions. The critical regions are near the center. You can see a little dash here. That's the center of the specimen. And what we see is, on the tension side, we get a very well-defined plus or minus 45-degree effect. On the compression side, it localizes in the center. All the damage occurs here, not here. The tension side had the largest strains toward the outside. The compression side, everything stayed large in the center with very small deformations on the outside. I was interested in why that occurred, so we actually measured the cross-specimen curvature, and what we found that it was quite large. Increased with fiber angle, as you see here. At 45 degrees fiber angle, the cross-specimen curvature was the maximum. As the end displacement increased. For the small angles, there was very little. It stayed fairly flat across the specimen. So that gave us a hint as to why things were different in this case for the 45-degree one. The last thing we did with this was to look, Dr. Rieschneider asked me specifically, is there any region where all the data can be collapsed onto one curve? And this actually comes, the results we got actually are consistent with the work of Ken Liechty and C.T. Sun, who did work back many years ago on composites. And yes, there is a region where if you plot effective stress versus effective strain, there is a region where all angles combine together to give you the same results. And here they are, that local region shows up here and shows up here on the tension and compression sides. Tension side is here, compression side is here, and they match quite nicely up to a few thousand microstrain. Beyond that, nonlinear effects take over, fiber buckling and other processes occur that separate the different fiber angles and alter the ability to correctly correlate those with one simple expression. And the effective stress and effective strain are given here, directly due to the work of C.T. Sun at Purdue. So that was the main thing we wanted to do out of this. And yes, there is a way to use effective stress and effective strain to coalesce the data, but it's only in the small deformation. Okay, one last one I'm going to talk about, buried blast loading. Model structures and scaling was the focus here. And I want to show you a video from Bill Forney that I think is extremely important. What you see here, you're going to see a buried blast take off from the bottom. There's a half-inch thick membrane that you can't see. It's sitting right on the surface. And what we're going to see is the sand moving up toward the membrane and interacting with the membrane. Okay, I stopped it. Now, it's important to note, this is not a dome. The theory behind a lot of this, the R-cubed theory that typically corresponds to the scaling formulations of Hopkinson and Krantz, assumes a certain type of shape to the interaction. Well, in the early stages, the blast hasn't even hit the membrane yet, and now it's something else. Okay? As it interacts with the membrane, it forms fingers. The fingers come up as a cylinder, and then after that, it begins to form a dome shape. The dome shape itself is of interest because that occurs later. But the question is, in the early stages where we're really interested, does that affect the ability to use scaling to predict what happens on the macroscopic scale? So to do that, we went into the lab at the University of Maryland of Bill Forney, used his sandblast facility. We set up the cameras as shown here. For the high rate folks in the audience, you can see over here where our two cameras are. They're outside of the sandblast pit. The lighting is a bunch of halogen lights attached to the side. Not all of them survived. I want to thank Bill Forney for continuing to pay for new lights. Okay. But the cameras had no problems. We did surround the cameras with a plexiglass enclosure, and they survived many, many times without any significant problems. The structures themselves are down below. This is the small one and this is the larger one. We took two specimen sizes that were completely scaled in geometry, mass, etc., according to normal scaling laws of Krantz and Hopkinson. From there, we asked the question, can we measure, and can we use those measurements to try to determine whether scaling will work or not? Okay, the actual explosives are shown here. The largest charge was 4 grams. The smallest charge was 1 gram. So So we use 4 grams and 1 gram of TN explosive. They're buried in the sand. The ones you're going to see are buried different distances, but typically depth of burial is very shallow, on the order of between 0.3 and 1 inch. So it's just below the surface, like the one you saw earlier. So the shallow blast itself was part of what we were interested in. Here's the specimen. Local. I'm not going to show this in detail. This is the pattern we used for the large specimen. This is the pattern we used for the small specimen. The dots were placed on by hand with a marker, and they worked fine. The background was painted with a epoxy paint. We kept it fairly damp before we ran the experiment so that it wouldn't delaminate. That's one of the issues you have to deal with. Delamination does occur at the high rates, and things are pretty well bonded, and they don't have time to begin to delaminate before you start the experiment. We also measured on the frame itself. We're also interested in the rigid body motion of the frame, as well as the deformation of the plate inside. And those are used to extract information about the global energy transfer. Here's the specimen, and on the left you'll see what it looks like, and on the right is a video showing the blast process in the sand. Oops, let me go back one. It's over. Okay, now the rest of this is just moving of the plate, and everything occurred in the first millisecond. After that, nothing happened. It was just sand coming out. So I'm going to stop this and go back and say, let's take a look at that first 2 milliseconds. Over here on the side is a 2 millisecond time frame. This is the center of the plate. Watch here is the out-of-plane deformation, as well as the curvature changes in the plate by just looking at it here. And a third experiment run later with the same parameters to see if we could see anything here as far as the deformations, looking straight down on it. What you see immediately is the blast started from the center and propagated out. You can see the shininess of the plate helps us see the waves propagating in here. And the waves themselves in the plate are actually showing up in the data. If you look carefully, you can see slight changes in the shape of the specimen are correlating with slight changes in color. Those color changes relate to the out of plane. So it first went to its maximum, dropped back down as the waves began to propagate and the process continued. We had further increases in displacement. From there, I want to look at the strain fields. Here they are. Here's the strain field in the X direction. Notice this large compressive region propagating all the way to the boundary, and then coming back with a rather large tensile region here. At the same time, the shear strains and the epsilon YY, which is the hoop strain, are not symmetric. Okay, that would be consistent with the way it actually was deforming, because it was deforming in a symmetric manner, so that the deformations in this direction would be different. Eventually, it led to a compressive region here at the base of one of those waves that slowly faded out over time. So you can see the kind of rich data you can. We used this to ask whether or not we could scale this. Scaling be used to take the data from the one test and convert it to the same result as the other one. So we use the unscaled data on the left for the out-of-plane displacement UZ, and on the right you see how we got with 3 tests, and it matched very, very well for both UZ and UX. It's well within the scatter band. So we are able to scale, even though the blast itself, over this time frame, which is several milliseconds, seemed to be quite a bit different. In fact, during the early stages, up to a millisecond, you'll see that they are almost exactly the same in here. So even though the shape of the blast loading didn't look like a dome, the results by looking at measurements on the top of the plate gave consistent results that could be scaled. In fact, it was scalable all the way out in time. It's also true in space. These are the spatial dimension now at 3 times. And you can see that the spatial shape of the surface changed, but we could scale them together, and they matched. So the scaling process could still be used for that. Finally, we look at the global measurements. That is, how high did the specimen rise during the blast, And in this, that's on the left for the height, that's the potential energy. And on the right was the impulse, the mass times the initial velocity. How did they compare? Small specimen, scaled small specimen, and large specimen. These should be the same. They're not quite. The scaled small specimen was slightly more impulse than it should have, or potential energy, height, and here's the impulse. Here's the small specimen, here it is scaled, and it does match pretty well with the large. It's within the scatter band anyway. So this gave us confidence that the scaling process seemed to be reasonably effective, even though the blast itself may not have been ideal. So let me put a summary to this, come off to other stuff. Full field measurements for this, for the blast case, gave us really a wealth of data that we used. Scaling we did this for all sorts of things, not just the ones you saw. We did it for accelerations and others, matched really well. And it looks to me like, even for relatively shallow buried blasts, the small buried explosives can be used for scaling. Okay, last part of the talk, I want to talk about the future a bit. We talked about where we've been, where we are. What about the future? This is one person's opinion, so I'm going to leave it at that. I want to talk first about future trends in DIC-based methods. What I see here is going to be multiple measurement system integration. It's already happening. It's happened for a long time, but it continues. Continued growth of parameter estimation approaches. We'll talk a little more about that. And then full integration of analysis and measurements for multi-physics studies. That's where I see it's going. Let's talk a little bit more about that. The design and development I'll come back to. That's at the very end. First, integration of multiple measurement system. Synchronized measurement with multiple measurement technologies. Some of these have already occurred. CT systems for slow speed events combined with stereo vision systems for slow speed events. Thermographic cameras for slow speed events or high speed. And then a range of other sensors. All these combined together in various ways to extract the wealth of information that's now available to us. It goes without saying that this is different than we've seen in the past. But the point is that it's doable today. Imagine putting all those together and finding out more than we ever knew before. Continued expansion of parameter identification methods. This is going on everywhere in the world. There are people in this audience that do it every day. I just don't see any way that this is not going to continue to grow and expand. You have some function, that's your theory. You have a series of data for that, and you want a series of parameters for your model. You simply combine those in a way to minimize some functional to extract the parameters that you want. And that vector of parameters could be huge. It's going to be something that's going to continue to grow. In materials characterization, it's already happening, but it could happen in a range of other areas. And I don't think that's going to change. Full integration. I believe that this is possible, that we can take specimens, subject them to a range of conditions, including electromagnetic fields, thermal conditions, mechanical loading, and acquire data throughout the process. Recently, a friend of mine did a lightning strike lab at MIT, where they literally subjected a specimen to a lightning strike with a huge electrical mechanical impulse, and still were able to acquire data from the cameras, and could measure the deformations as the lightning struck the composite throughout the process. It's coming. This stuff is coming. The question is, how much imagination do we have? Finally, I want to talk about integration with design and development. This is my favorite topic in this, because it's so different. And it's my perspective on this. Let's imagine we want to start with a priori information for a design process. Okay? What does that mean? That means we need operational conditions, we need material properties, and we need geometry. But down in here, we could use material parameter identification from whole field data and novel experiments to extract a wealth of new information for these materials. So we can integrate what we're doing now into the design process. Same way with geometry, size and shape. We can measure shape all day, and with CT systems, we can measure internal shape at the same time. Put those together, and what do you have? You have a priori information set that's far greater than we've had in the past. And it's experimentally measurement-based, not guesstimate. From there, you go to your current design. You make your first design, you assemble it, you're ready to do your proof or certification experiments. There you have to validate things because we need a model for this. We don't want to run experiments any more than we have to, of course. But we have whole field experimental data that we could use to do the evaluation of that design test. With that, we can improve the model. And these two would then be integrated together in a way that would provide us with a platform that's experimentally validated for design. From there, we simply do the rest of the process for design. We test to determine whether or not it's going to work. We determine whether we met the criteria for the experiment. If we haven't, we have to do design optimization. Here is where the link is. I think this is where the work would be done in the future if you're going to do this, is in this design optimization platform. Because if you didn't meet it, you've got to iterate this. And that means you've got to come back to here, modify the geometry, modify the material, even modify the operational conditions in a manner that's developed in the optimization process. Is that available today? Probably not. Could it be done? Yes. A friend of mine, Professor Gerdahl, who came from the Delft, is working on this right now for an aeroelastic problem, where he's modifying geometry with known material properties and looking for an optimum geometry to minimize drag under very specific conditions. But that's an optimization process which led to weird designs. And it's all driven by the ability to make the measurements too. Oh, so the final design would be the end of this. Once you're done and you got it, then you're there. But out of this, there are two things that I'd point out. Here, here, and even the third one, here, is where DIC could make a contribution. Or whole field methods that make measurements under conditions that are unusual or strange or not perceived to be possible in the past. So, in closing, image correlation methods provide a unique capability to make measurements required to implement such simulation measurement design concepts. So in the end, I would say that there are two things that require efficient and robust optimization methodologies. First, you've got to be able to put things together in a way that the model can get the appropriate parameters. If you do that, then you've got to optimize the whole process to make sure that you know that things are going to be done properly and try to find the best optimal design for your condition. That's going to require work. So successful implementation of these does offer the possibility of removing some of existing testing standards. Do we really need just 3 sigma for the yield stress, saying we got to meet with factor of safety of 3, 1/3? No, I don't think so. And I think that's already being done in a variety of areas, but now we can put it into a robust structure that could be used by everybody. The one thing that's got to be done is professors have got to still be around because the educational level has got to be high. You can't do this without understanding what you're doing. There's no doubt in my mind it's feasible. The question is it something that we can prepare our students for to meet this challenge? Okay. Upcoming DIC-related activities. I'm nearing the end of the talk. I just completed an article for Applied Mechanics Reviews. Please feel free. It does talk about some of the things I've done here. Plus, we are developing a special issue in experimental mechanics for DIC that focuses on that. And a second edition of the book is under development. So a series of us, Professor Hild and Professor Dr. Roy and others, are working on the next edition of the book. And we hope that it'll be out sometime next year. Here's my students that have done all the work over the years. I still have 2 students. I'd like to recognize them. Ximing and Jingzhao are my 2 current students. I want to thank them along with all the others, including Hugh Bruck and Jeff Helm and others that have been involved over the years. The references, and I thank you.